Salam sejahtera semua. Hari ini saya nak ajar simple pendulum. Okay, pendulum di sini dia berikan kita satu gambaran di mana katakanlah ini adalah satu siling. Okay, satu siling, dan di siling tersebut telah diikat dengan tali di sini, dan tali tersebut bersambung dengan bandul, ataupun kita panggil dia pendulum lah. Ini pendulum. Okay, and here at the center, what you call is here as equilibrium position. Equilibrium position where x is equal to 0. Okay, and here bila eksperimen dijalankan, cara dijalankan adalah dengan caranya bandul ni akan bergerak daripada ikut arah ni. Sekarang ni macam saya tunjukkan sekarang ni, bandul ni sekarang bergerak daripada center ke kanan. So apa yang jadi, dia akan bergerak kanan and then balik kepada equilibrium position, and kiri and then balik pada position center, balik sini. Okay, dan benda ni akan berlaku sampai dia berhenti. Okay, sampai dia berhenti. Tapi untuk yang sample pendulum ni, dia ada bagi condition yang mana di sini conditionnya adalah there is no friction. Maksud no frictions, that means that there is no air resistance. So what does that mean? Means that bila when we conduct an experiment on this simple pendulum, so what happen here is when we release the pendulum, it will start to move back and forth non-stop. Okay, it will move back and forth non-stop. Dia tak akan berhenti until we apply another force, okay, which makes them to stop moving lah. Okay, so here is the condition. There is no friction, that means no air resistance. Okay, and at the same time, when there is no friction, this is where we say that there is no energy dissipation, which means that the object, the pendulum, okay, the system will move without losing any energy. Okay, that means that the system will keep moving until when? Sampai kiamat lah. Okay, sampai kiamat, ataupun sampai when we interrupt the system, maybe we stop the pendulum, okay, or anything else lah, to stop the system start moving. Okay, so here in the experiment here, at first the scientist, okay, wants to calculate how much from the equilibrium position to the certain this place, how much does it the pendulum travel, how much is it. Okay, and from here we have what we call is the theta, atau what we call is as the angle. Okay, so from here theta, and we have S and L, which is the length of the string. We can actually calculate S. So how do we calculate S? We use the formula length of the arc, which is S equal to R theta. Okay, which is R is the length of the spring, as you can see, and then theta is here and S is here. So when we derive formula, so S is equal to S L theta. Okay, so here is the formula to find the displacement. Okay, here this is what we call as a linear displacement. Okay, right now as you can see, L is the constant. Okay, which means that when the pendulum start to move, okay, back and forth, L does not change, which means that when the object start to move, the length of the spring does not change, which means that length of the spring ni dia tak akan panjang waktu berjalan ataupun makin pendek waktu berjalan, dia akan tetap sama je. So apa yang berubah kat sini when the system start to move is S and then theta with the respect of time. when bila masa berubah, contoh at here is at the time 0, and at the time 1 second, where would it be? It might be here or it might be there. Okay, that means that theta and s can be changed in the function of time. So here is means that s with the respect of times is equal to L theta with the respect of time. So always remember that L is a constant, theta and S is the manipulative variable. That means that they can change, they can change in the respect of time, in the function of time, right? So now let's move on to the force distribution on the system. So as you can see, we have the pendulum, okay, which is over here. We have the wave, which is directed to the center of the earth, always directed to the center of the earth, which is downward. And we have another one which is right here, okay, which is what we call as tension. Okay, tension is a force that is inside of the string, okay, inside of the string, and always directed to the ceiling here, and at the same time always directed opposite to the ball here, okay. And here we have another force which is directed. I will draw for you, okay. I will draw you, okay. Draw. So here is another distribution force, an additional distribution force. So here is the force which is called as FL, okay, and over here we have the force which is called as FS, okay. Now always remember that this right here, this force right here is perpendicular, this force right here is selari dengan this one, okay. So that means that when it is selari, okay, that means that they have the same direction over here. And always remember that this force right here is always perpendicular, which is 90 degree to the, which is I say that FS is always perpendicular to the FL, okay. So always 90 degree. So that means this is FL, right? So here is also FS, since that they are parallel to each other. Parallel, bukan selari in Malay lah. Okay, here we can at the same time, here is the theta. This is theta, okay. Theta here always say that always remember that theta at this side is always same as this one. Why? Because here we have the straight line, okay, and here also we have the straight line which is parallel to this one, and then at the same time we have another line which is parallel also to this one. So that means that we have the same amount of angle with this one, okay. So we can make a new equation for the FL, which is, as you can see, we have the hypotenuse, which is W. Okay, I'll write for you. So hypotenuse is W, and then we have the opposite of the theta, which is FS, opposite FS, and then we have the adjacent, which is over here, which is FL. So FL. So from here, okay, from here we can relate this to the trigonometry, which is sine, cos tangent. Okay, so sine theta, cos theta, tan theta. But at this one, we will not tan theta. This one we use. Okay, we will only use sine and theta, sine theta and cos theta. So tan theta, we know that it is opposite over hypotenuse. So what is opposite? Which is Fs over hypotenuse, which is wave. So to get Fs will get equal to W sine theta. Okay, and cos theta is equal to adjacent over hypotenuse, which is Fl over wave. So we will get Fl is equal to W cos theta. Or we can derive more, which is wave is equal to mg and then sine theta. Same here too, mg cos theta. Okay, now since we got the equation for this, both of them forces, okay, now we will relate them to the second Newton's law, which is, okay, second Newton's law. This is the force distribution. Okay, so first we are going to talk about the at y component. Okay, so here what we have here is the y component, which is the t, which is directed upward, will minus with the Fl. So t minus Fl will be equal to ma, always equal to ma. Okay, now let's see. Since that we have the pendulum, which is always move back and forth, and at the same time, which means that back and forth means that the object will move to the right and to the left, not even move to the upward or downward. So that means that there is no movement which is directed upward or downward. So that means that acceleration at the y component is equal to 0. So we will get t minus Fl equal to 0. So tension will be equal to Fl, and then tension will be equal to mg cos theta. Okay, as the question will ask you if how to find the tension of the string, we will use this formula to find the tension of the spring. Yeah. Okay, now we'll move on to the y component at the x component. Let's see what is the force related to the x component. So as you can see here, we have the x component, which is Fs. So that means that Fs is equal to, always relate to the second Newton's law, which is ma. Okay, so Fs equal to, since that we know that the object is moved to the right and to the left, that means that the acceleration on the x component exists. So we can write that ma, we can write it as ms double dot. Why? Because we know that s is a linear displacement. So linear displacement, we want to turn it into an acceleration, we have to do a second order differentiation, right? This is for reminder. Okay, remind back. So we know that s is displacement, which is equal to s x. Okay, same as the simple harmony equation, and we have s single dot, which is velocity, or x single dot, and we have the s double dot, which is acceleration, which is equal to x double dot, or maybe y double dot. Okay, but since here we have the object is moving on the x component, so we will relate it to x. Okay, we relate to x. Okay, that's why I say ma is equal to s double dot. Okay, this is a. Okay, now here we want to find how do we obtain the acceleration, the linear acceleration. How much this pendulum accelerate to get to the point. any point, maybe here, or maybe more than here. Okay, so we'll break through this formula. So Fs is equal to here, W sine theta is equal to ms double dot. So break through W, which is mg sine theta, is equal to ms double dot. So here we have the same, so we have cut off. So we will get s double dot. Oh, sorry. Since that Fs is directed to the left, okay, to the left, that means we will obtain Fs as a minus here. Sorry. Okay. So we will get s double dot is equal to negative g sine theta. Okay. This is how we calculate the linear acceleration. This is linear acceleration. But as you can see that this linear acceleration can be manipulated when the theta is changeable. That means that s double dot can be changed, okay, when theta is changed. Okay, so now we want to make a little bit further experimentation, which we want to make this theta to become acceleration. Okay, this is theta. Theta is known as the angle, right? We know that, and they present theta also as the angular displacement. Okay, so they want to make angular displacement as a angular acceleration. Okay, now to get the angular acceleration, we have to differentiate theta differentiate theta 2 times to get the angular acceleration. Okay, so when we integrate theta, okay, when we differentiate theta 2 times, okay, first we cannot differentiate truth from here. No, we have to differentiate from this equation. Okay, so we know that S is equal to L theta. So as I said that this both, okay, can be changed in a function of time except this one. So that means S with the respect of time t is equal to L theta with the respect of time t. Okay, so we differentiate both of these equation 2 times, okay, to get acceleration. And so what we get here is we will get S double dot t is equal to L theta double dot t. Okay, now we will relate this equation inside this equation. Okay, so what we will obtain is we will get, okay, so we know that S double dot is equal to negative g sine theta. So we will get S double dot as the L theta double dot. So L theta double dot is equal to negative g sine theta, and we will get theta double dot is equal to negative g over L sine theta. This is how we calculate the angular acceleration. Okay, now here when you read more about this equation, they say that sine theta can be approximate as theta if, okay, there is condition to get this one. Okay, condition is for this: if the theta must be less than or equal to 30 degree, or theta must be less than or equal to pi over 6 radian. Only this angle can be used to apply this new equation, which is theta double dot t is equal to, so sorry, you don't have to put t here, okay, is equal to negative g over L theta. Okay, this equation only can be applied when the theta is less than or equal to 30. Okay, you cannot use this formula if theta is more than 30, because what happen is that when you use this formula when the theta is more than 30, it will be error. The calculation will be error. I don't know how to prove this. I've read about it, about this one. If you want to look more depth about this one, I suggest you to search internet. But if you do want to, you can PM me and talk about this with me. Okay, this formula can be applied when theta is less than or equal to 30 degree, or theta equal to or less than pi over 6 radian. You can apply this formula if the theta is more than 30. Okay, please bear in mind here. Alright. Okay. Now, let's move on to more. Let's go more depth about this theta double dot. So, as you can see, theta double dot, okay, is equal to negative g over L multiplied with theta. Okay, this formula has a relation with the simple harmonic motion, which is x double dot is equal to negative omega square x. Okay, so you know what happened here is that omega square is equal to g over L here. Alright, so here we will get omega is equal to square root of g over L. Here is another new way to calculate the omega or angular frequency. So here we have one, and another one here is we have learned in the previous lesson, which is omega equal to 2 pi over t, and another previous lesson which is omega is equal to square root of k over m. So here we have three different ways to calculate the omega. Okay, so please bear in mind here. And also when we know when we talk about omega, there is a relation with tension. There is a relation with the period. So to calculate period, so period is equal to 2 pi over omega, right? So always substitute omega with square root g over L. So we will get 2 pi times square root of g over L with the power of minus 1, or we can write 2 pi times 1 over square root of g over L. It is still the same one, okay? You can use it to calculate period. Okay, and if you want to calculate frequency, yes, it's the same. So f equal to 1 over t, and then you substitute t with this one equation. I think you can do it by yourself. Alright. Okay, now from this equation, okay, we have omega, we have omega. Okay, we can form an equation, and is the equation for the simple harmonic motion, okay, which is theta t is equal to a sine omega t plus pi naught. So a, we know that is the maximum displacement, which is theta maximum. Okay, and omega is square root of g over L. So here theta t is equal to theta max sine omega, which is square root of g over L times t plus pi naught. Or you can use square root of k over m. It is still same. Okay, or maybe 2 pi over t. It is the same. Okay, and for the velocity, which is theta single dot, it is still same. You have to differentiate this equation. So we will get square root of g over L times theta max, and then sine will become cos, and then square root of g over L t plus pi naught. And the last one is the acceleration, which is theta double dot with the respect of time t is equal to g over L multiplied with theta max times with the negative sign. Sorry, I'll put this negative here, sine, and then copy back, so g over L times t plus pi naught. So here is how we use to form a simple harmonic motion. Okay, here is the equation. Alright, it's okay, don't worry, I will post these notes to you so you can do a refer. You can refer these notes when you watch my video. Alright, see ya, good luck.